Hi everyone, in this video I wanted to go over how you can design inductors and transformers using HFSS for on-chip power amplifiers, for example. The way I want to do this, I want to make the design parametric so that you can quickly change variables and simulate sweeps, and also use optimization tools using MATLAB and HFSS, which I'll cover in another video, to optimize different designs. So let's get started. First, what you want to do is open HFSS. You should start with a new project, and then you want to insert an HFSS design. Let me rename this. So we can call this Coils, and I'll rename this to Coil Inductor. Okay. The first thing we want to do is add the silicon substrate and the silicon dioxide layers. So click on the box, and you can either hit F3 if to remove the prompt that came up in case you want to draw it by hand, or if you want to draw it using the prompt, then every time you hit a box and you don't get the prompt, you can hit F4. Okay, so let's take this box. I'll call this silicon. We can make it minus substrate width divided by 2 minus substrate length divided by 2 and substrate height minus substrate height. I'll make this 100 microns, and 250 microns. Of course, we'll change these numbers later based on the size of the inductor, but for now, these are the numbers I'm putting in. Okay. So once we're done with silicon, we'll assign the material later. For now, I'm just making the silicon box. And then we also want to add the dielectric layers. So in this case, I'll just add 1 or 2 just as a demonstration. But in reality, you may want to add more based on what the PDK that you're working with. So I'll call this aux1 thickness. So let's make this 500 nanometers. Call this oxide 1. And then you can make the second oxide, which starts at the height of the first one. And this one, let's say, has a thickness of 2 nanometers. And then the third oxide, which has a thickness of, I don't know, 5 nanometers, let's say. Okay. So we have, sorry, this should be oxide 1, oxide 2. This should start at oxide 1 thickness plus oxide 2 thickness. Okay. So just check that. Oxide 1. Oh, there should be 2 micrometers, my bad. 5 micrometers. Okay. Now it makes sense. We have our silicon, oxide 1, oxide 2, and oxide 3. Typically, you may also have a nitride layer, which you want to include in case the inductor doesn't have any ground plane underneath it or any shielding. So let's just hide these layers, and then now we can start with the more interesting part, which is drawing the actual inductor. Okay, so since we want to make it parametric, it's not very straightforward, but I've done some simple geometry calculations to make it much easier. So let's start by making one section of the hexagon. So I'm going to make a hexagonal inductor because that would pass DRC rules. So I'll just make a box, and then from this box I'll start drawing out the values. Okay, so let's say the x position is inner diameter divided by 2 minus section length divided by 2 and M9 elevation. So metal 9 elevation, here I'm using M9, can be any metal layer. So I'll just say it's 5375 nanometers. And the section length for now, let's just make it 20 microns. M9 elevation, I thought I already entered that, but maybe not. Okay, 5375 nanometers. I think I made a mistake here. So, okay, inner diameter should be 50 microns, let's say. Okay, so let's go back and we'll call this the line width, which I want to be 2 microns for now. Y size is the section length, and Z size is M9 thickness. M9 thickness, let's just say for now it is 3400 nanometers. Okay, so this is the first section. What I want to do now is make a hexagonal spiral out of this. It's very easy. You click on the section. Let's call this actually section 1. Click on the section, right click, edit, duplicate around axis, 45 degrees and 8 sections. That becomes a hexagon. But the problem now, of course, is that they are not joined. For that, the length of this line has to be correct. So since I've already calculated it earlier, I'll just enter the value. It's pretty simple geometry. So the section length needs to be 1 divided by 1 plus square root of 2 times inner diameter plus 2 times line width times tan 22.5 degrees. Okay, so with this now you have the hexagon that exactly touches. Perfect. Okay, since I want to make this a 2-coil inductor, I want another coil around it. So the way you can do that is pretty simple. You just take this and make a copy. So you have a second section now, and this section has a different length, of course. I'll call that section 2 length. Let's just make it 25 microns for now. And the position also changes. So now the new position of this one is going to be the inner diameter plus line width plus gap. And I'll make the gap 2 microns. And you also want the length to be the section 2's length. Okay, so now you see how this works. We need to change this so that even when you make copies of this, they again connect together. And that's again pretty simple. So what you can do is just make a copy of section length. And now instead of using the inner diameter here, we need to have inner diameter plus 2 times line width plus 2 times the gap. Makes sense, right? Because you have one line width here and one gap here, one line width here, one gap here. So the inner diameter is now bigger by that much. Is that right? Okay, let's see. So I say edit, duplicate around axis 8 times. Something is wrong. One plus 1 over square root of 2 times inner diameter plus 2 times line width. Oh, sorry. This should be plus 2 times the gap. Okay. So now you see we have the 2 spirals. Now what we want to do is we want to make a transition so that we can cross over these spirals. Doing that is actually the trickiest part. Let's see how we should do that. So what I want to do is I just want to make a regular box. I'll call this minus transition width divided by 2 minus transition length divided by 2 and 9 elevation. We'll just put some numbers in for now. 5 micron, 5 micron, transition width, transition length, M9 thickness. Okay. What I want to do is I need to make sure that the length and width of this is correct. So for example, just say the width is 5 and the length is 2. Okay, and we can rotate this, arrange, right click, edit, arrange, rotate by 45 degrees. Actually, let me make it minus 45 degrees. Okay, and then we also want to move this. So edit, arrange, move. I hit F4 and then I move it by this value, diameter divided by 2 plus line width plus gap divided by 2. Okay, so now we see that it's gone up there, but I want to make sure the length of this is correct. So we need to again do a calculation. I've already done the calculation, so I'm just going to put the value in. So the length of the transition needs to be line width times 2 times square root of 2 minus 1 plus square root of 2 gap. Should be the length, the width, not the length. And the actually no, this should be the length, and the transition width should be the same as the line width. Okay, perfect. So now we see that this line ends exactly at that point, and this point ends exactly here, which is exactly what we want. And we also want to make another transition, so I just did copy paste, and I want to rotate that the other way, 45 degrees. All right, so this kind of starting to look like a bit of an interleaved inductor, which is exactly what we are going for. Just to make it a little bit more obvious, I can bring this down. So we see that this is what it looks like. Okay, a few more steps before we're done with the transition. We need to make a subtraction box to subtract out this part. So I'll hit F3, make a box. Of course, you also need to make this parametric. So the way we can do that is I make a box, and then I need to define the position to be minus transition length divided by 2 divided by square root of 2 minus transition width divided by 2 times square root of 2 comma inner diameter divided by 2 comma M9 elevation. Okay, and the length should be, the xi should be transition length divided by square root of 2 minus transition width divided by square root of 2. Made a typo somewhere. Okay, we need another bracket here. Okay. And this should be 2 times line width plus gap and M9 thickness. Okay, so now you see that we've made a box that exactly touches these 4 points. Okay, the next step is to select this, select both of them, and also select the box and subtract. But you only want to subtract the box from these 2 sections. So now we end up with a transition that looks like that. Still not good enough, of course, because these 2 lines are crossing. So we need to move one of these lines up and then bring it down. You need to make a bridge, basically. Okay, how do we do that? So the way we do that is I will select only these components, hit this, so you only see these. So to select faces, what you want to do is hit F on the keyboard, click on this face, and to go down to descend to the bottom face, you hit Control B. And then hit Control, select this face, descend to the bottom face. Now we want to make a via here. So we say Edit, Surface, Create Object from Face, Edit, Surface, Thicken Sheet, and minus via length. And I want this to be 3 microns. Okay, great. This is actually not enough. One more thing we need to do is we want to make sure that the via is the right size. So the way to do that is we make a copy of these two boxes again. Control C, Control V, only view those boxes. And we need to move these faces by a certain amount. So edit surface, move faces along normal, minus line width times tangent of 22.5 degrees. It'll make sense why we are doing that, but we just need to do that for now. Okay, coming back, so we have, I'm hitting O again to select objects instead of faces. So let's select all of these, make these visible. So we have this section, we have this section, and we have this section. These are the three important sections. So now what we want to do is select this and this section, make them visible, and we want to move these faces back. So select the two faces, edit surface, move faces along normal, and we want to move this back by minus the via length. So now we have something that looks like that. Okay. All right. Now again, select all the objects, come up here. Okay, so now what do we have? We have this section, and this section. So you want to unite these, and then let's move this up. So the way to do that is you right click, edit, arrange, move, and then now it's in this mode. I want to change it to the value mode, so you can hit F4 to do that. Excuse me. And then let's say we go up to M10 elevation minus M9 elevation. Let's say M10 elevation is 9575 nanometers. Okay, so you see that now this is moved up. Right? Okay. We also want to move these up so that they connect to the top surface. One more thing you can do is you can change the height of M10, this section, by hitting the top face, then say edit, surface, move faces along normal, and we want to move this by M10 thickness minus M9 thickness. And let's say M10 thickness is 1450 nanometers. Okay, that's what that looks like now. And then these two sections that we made will act like vias. So what we need to do is we'll make copies of them first. Yeah, we can make copies. Copy paste, hide the copies, and then we want to move these. Edit, arrange, move that by M9 thickness, and we also want to move this faces down. Edit surface, move faces along normal, and we want this to be M10 elevation minus M9 elevation minus M9 thickness. Is that right? M10 elevation minus M9. Oh, no. 2 times M9 thickness. Same for this guy. Okay. So now you see that this box acts like a via. Of course, we can't make individual vias because that would take forever to simulate. I'm just making a via cube. And you can find what the effective conductivity of this should be by simulating a set of vias and then finding what the conductivity is of what the equivalent conductivity is. Anyway, so let's view everything. So now you see that the bridge is ready, right? We have one layer going down, one layer coming up. Of course, you can also use the same thing to move this to a bottom metal layer and then go across. It's the same idea. Okay. Now we need to unite a few parts. So we want to unite this and this. Unite. And you also want to unite this section and this section. Unite. Okay, that's it. That's the transition. So we can test it a little bit. Maybe we can test it later. So let's just move on. So the next thing I need to do is I need to add feed lines, 2 feed lines here that connect to the inductor. So let's do that. The way to do that is, again, I'll make a box. This is kind of a easier way to do it. Okay, so I'll say feed separation divided by 2, comma, and the length to be, no, the position needs to be minus inner diameter divided by 2 minus 2 times the line width minus the gap, comma, M9 elevation. So let's say feed separation is 20 microns. Feed separation. And the y size should be the feed line length. Define this later, but for now I'm just going to call it the feed line length. Minus 10, and let's call this M9 thickness. Done. Okay, this feed separation actually is too much, so let's reduce it to 5 microns. Okay, so now you see that we have the 2 feeds coming in. We have something here which will look like 2 feeds soon. One thing I want to change is I want to actually make this just one line. Okay, so now what I want to do is select this face, select this face, control, select this face, and then say edit, surface, create object from face, edit, surface, thicken sheet, line width. So now you see that we have the original one and then these two. And then all you need to do is select that, control, select this, and then subtract them. Alright, so now you see we have our 2 feeds coming in, going into these sections. So this looks a lot like our interleaved inductor. Okay, almost done. We need to make a few more features. So one feature that we need to add is a ground wall. So let's say I want to add a ground wall around it. And we can do that pretty simply. Make a big box. And I say minus wall weight divided by 2, wall length divided by 2, comma, M9. Even these values will change. I'll just say 50 micron for now. Wall weight, wall length, M9 thickness. Okay. That's one box. I want to make another box. Minus wall weight minus wall thickness. Wall thickness. Thickness of the wall, let's say 5 microns plus 2 times wall thickness, 2 times wall thickness. And so now I have 2 boxes, this one and this one. Of course, I want to subtract them. Okay, that makes the wall. The next thing we want to do is to make an indentation in the wall so that the feeds can come in and we can assign ports there. So let's do that. So what's the best way to do that? Let's see. Okay, the easiest way is again to just make a box. Let me just make another box. So we want to say this is minus feed ground width divided by 2 minus the wall length divided by 2, comma, M2 elevation. I want the ground plane to be at M2, for example, plus M2 thickness. So feed ground width, let's just say it's 10 microns. and M2 elevation, let's say it is 945 nanometers. M2 thickness, let's say it's 220 nanometers. That should be 220. We need to change a few things here. Feed ground width minus wall thickness. And here I want to say it's M9 elevation plus M9 thickness minus M2 elevation minus M2 thickness. No, this should be M9 thickness. Okay. The ground wall actually should be a bit different. So this should be M1 elevation, which is say 590 nanometers. And I want this to be M1, M9 thickness. I want the ground wall to be all the way from M1 to M9. So let's say the total thickness of this is 8185 nanometers. Okay, that looks like a wall. Of course, I also need to do that for the subtracted box inside it. Okay. So now we subtract this wall from the feed box. Subtract, done. Okay, feed ground width, let's make it 20. Okay, so that's what that looks like. There is an issue now. One issue is that if I change, for example, the wall width or the wall length, then the feed lines don't extend, but we do want that to happen. So what we can do is we can make the wall width into a variable. So I want to call the wall width as this inner diameter plus 4 times the line width plus 2 times gap plus 4 times the wall separation. And the wall separation is, separation from this point to the wall. And I'm making it 4 times. So for example, in this case, I set the wall separation should be 10. So the separation between here and here should be 20 microns. Yes, 20 microns. Make it easier, I can change the units to micrometers. Okay, that's the wall width, and I want to do something similar to the wall length. Wall length. I'm just going to say wall separation times 2 because I don't want these lengths to be too long, so that's why. Wall separation, if I make it 5, you see that it comes closer. And I also need to define the feed line lengths to be a variable so that they scale correctly with the wall separation. So feed line length, let's say it is wall sep plus line width plus wall thickness divided by 2. So they stop exactly in the middle of the wall. That's pretty much it for the drawing. Now we need to assign some ports, assign the materials, and set up the simulation, and then run it. So let's do that. A cheap way to make the ports is just select the two faces, right click, edit surface, create object from face, edit surface, thicken sheet, let's just say 1 micron. And then what you can do is select the bottom faces of this and this, and then you extend them down, edit surface, move faces along normal. You want to extend them down by M9 elevation minus M1 elevation. Okay, and then you can select this face, go back, select this face, Control B, edit surface, create object from face, and then you can just delete these boxes that we made. So that's a cheap way to assign a lump port. It's faster this way, I think, rather than defining this by equations. Anyways. Okay, so let's just take a look, make sure everything is okay. So we see that the port is touching both metals. It's not extending beyond the metal. The transitions look good. Okay, that's about it. So we can go ahead and assign the materials. So in this case, I'm just going to assign all of these to copper, but in reality, you should not do that. So let me hide these. In reality, you should use the actual conductivity of each material, and including the vias and each metal layer. But just for simplicity, I'm just going to assign copper now. Okay. All right. We can also unite some of these layers. So if you select from the right side, it'll select everything that is touching. Like this, select this, unite that. Also unite this part. Okay, so now you see that looks more like an inductor. Give it a nice color maybe. Give this maybe blue. This is a different metal layer, so we can give it a slightly different shade. Okay. Okay, so we see that the oxide layers are not actually covering the material, so maybe the values that I chose were not very good. So let's just make all of them 2 nanometers, 2 micrometers, 2 micron. Let's say this is 4 micron, 6 micron. Okay. It's just an example, so it's not super important. And we can increase this to 500 microns and 500 microns. Okay, so let's go back here. And let's arrange some of these materials so that this is all copper. We can assign these to silicon dioxide. Silicon dioxide. And silicon can go to silicon. Okay. Of course, you have to use the right materials here. This is just an example, so I'm just showing you for some materials, but okay. The next thing we want to do is I want to arrange these variables so that I have the variables that I'm going to change in the beginning. So the most important parameter is the inner diameter, then the line width, then the gap, and then the via length is also important. Wall separation is important. Wall thickness is important. The field separation is important. Let's actually move this up. What else? That's basically it. So these will be the parameters that we can sweep. Yeah. Okay. So let's just test it and see how these parameters change the design. So let's say I make the inner diameter 50. So you see it scales up. It can be a little bit tricky to get the via depth to be correct, like the via length to be correct. So for example, let's say I make the line width 5. So you see it starts showing some bugs here. So you need to make sure this length is also large. So one simple way is to just make it the same as the line width. Right, so then even if I make this small, now it may be too small, but it's okay, I think. So if I make the line width 10, then you see that the vias have also grown. You can also increase the gap. Seems like there's a bug there. Yeah, there is a small protrusion here. So I mean, there are these small bugs. It's not too hard to get rid of them if you want to do some extreme designs, like something very small or very thick. But for traditional widths and lengths, it's good enough. So let's say if I go 5 microns and 5 microns, then you see that it's all perfectly fine. Yeah. Okay. The feed separation is 5. There was another parameter which was feed ground width. Yes. This one. This is also somewhat important. So we can say that this is equal to 2 times plus gap plus 5 microns. So that it's separated by about, or we can say it's plus 2 times the line width again. So this will be one line width, this is another line width, and that's one gap. Okay. Wall separation, if I make it 10, becomes bigger. And of course, you can change the wall separation for the W, the width of the wall and the length of the wall. You can make them separate. I can make this 8, for example, or 6, or even just a square wall. Depends on what you prefer. Now let's just make it 6. And we can make the wall separation a bit smaller, 5 microns. Okay, so you see these ports. We have the copper, and we have the wall. Okay, that's about it. We need to assign the excitations now. Select this material, select this object, right click, assign excitation, port, lumped port. Oh, I need to change the solution type. Solution type modal, hit OK. Assign excitation port, lumped port, 50 ohms, integration line. You can either assign up or down. Just be consistent. Yes. Okay. All right. The next thing we want to do is add an airbox. So you can hit right click, create open region, and select the operating frequency. Let's say 220 gigahertz, and then say OK. So that should make an automatic airbox based on what's the frequency you're working at. Okay, so we have a boundary, we have our excitation. We don't need to define any meshing here specifically because the sizing of all the structures are fine and we don't have any strong fields anywhere. We need to add an analysis, so hit solution setup advanced. Let's say I want to simulate 220 gigahertz, 20 passes, delta S 0.01, minimum number of converged passes 2. Say OK, and then it will ask you for a frequency range. So let's say we want to simulate from DC to 350 gigahertz, 401 points. We can also save the fields, but I'm just going to skip that for now. And you can leave it as interpolating if you just care about the S parameters. Okay, so we set this up and hit simulation, validate. Okay, so then it'll say a lot of your boxes are touching. So then you can just go right click here, go to design settings, and then say enable material override. One more thing you can see here is you can export S parameters directly after each simulation automatically. So you can say export touchstone file after completion, override, and then select a folder where you want it to be. For now, I'm not doing it, but you can do that. Okay, validate, it's all good. Clear this, and then run the simulation. So once it's done, I will continue. Okay, the simulation finished a few minutes ago. I also set up some results. So let me show you how to do that. Once the simulation is done, first you have to make sure that there were no errors and it ran smoothly. So it says normal completion of simulation. Hit right click, create model solution data report, rectangular plot, and then we want to find the inductance. So for that, what I did is I selected Y parameters, and then you can go in here and then type imaginary part of 1 divided by Y11 divided by 2 times pi times the frequency times 10 power 12 so that it's in picohenry, and then just say new report. I also want to find the quality factor, so that would be s of imaginary part of y11 divided by the real part of y11. That's it. So that's what I had earlier here. So I'll just delete those, and then you rename this to inductance and quality factor. These are the two values you really need. Uh, so we can take a look at the inductance. Add right click marker, add X marker, and you see that there's a resonance at around 80 gigahertz. Before that, it's an inductor of about 300 to 350 picohenry, and the quality factor uh, is around 25. Of course, it'll get worse when you change the, instead of using real copper like copper, you use the material that is available in your PDK. But this basically concludes how to design an inductor. I'll quickly go over the transformer, which is very similar to this. You basically just make another coil facing the other way um, on the lower metal layer. So let me just quickly do that and come back. Okay, coming back, basically what I've done here is to convert the inductor into a transformer. So we had this inductor, I made a copy of the file. I called it a 2x1 transformer, and I didn't do anything special here. All I did was that if we hide this layer, so I just made another, you can also hide this transition and the vias. So I made another hexagon, and as I did before, I just cut out this part and made the two feeds onto this side now. And I also added a center tap on the left side, which goes down and touches the ground. And I also added a center tap for the two coils. So you see this is a center tap for the top layer and a center tap for the bottom layer. Make it easy to visualize, you can change the transparency to 0.5. So now you can see what's going on. Okay, I also made this second inductor, the one below it, parametric. So you can also change the diameter of this one and the parameters of that one. The next thing I did was that I added these two extra ports on this side, the same as the other inductor, port 3, port 4. And for the center taps, I added a boundary condition. You can also make these ports, but in this case, I just did right click, assign boundary, and made it perfect E. So it's like a metal basically. It's just going to short it out to ground, the center taps. For RF, it doesn't matter, but typically you want to add some biasing from here, then you have to go down and you can connect it to the biasing network. Okay, so then the next thing I did was that I just ran the simulation. So you can see that there are 4 ports, 1, 2, 3, 4. I ran the simulation and I exported the S parameter file. So we want to see how we can extract the model values. If we go and say inductor model, no, inductor transformer model, for example. So this model. So if you want to find out from this transformer what is the value of L1, L2, K, and also the quality factor of L1 and L2, then what you can do is you can go to yeah, you have to export the S parameter file. So just go to design settings, as I said earlier, export on completion, export it. And once you export it, you can import it into ADS or Cadence. In this case, I'm using ADS, so I'm just going to show you with ADS how to import it. So what I have here is the 4-port S parameter file, port 1, port 2, port 3, port 4. If you don't know how to set up ADS, there are literally hundreds of tutorials on how to set up a simple S parameter simulation in ADS. You can also use Cadence for this, it doesn't make a difference. So all you have to do is get the S parameter file, put it in here, put 2 ports, and to compare it to the model that I showed earlier with L1, L2, Q1, Q2, and K, you can add 2 inductors, in this case it's L3, L4. You can set their inductance values to L1 and L2 in picohenry. And the resistance, the series resistance would be given by this equation. It's a function of L1 and Q. The same goes for the series resistance of this part. You can set up variables to be L1, L2, K, which is the coupling coefficient, which is defined by this mutual inductance setup that you can add, where you can set the 2 inductors to be L3, L4, which are the names of these two, and Kc, which is the variable, which is the coupling coefficient. Then run the simulation. In this case, I'm just running it from 40 to 60 gigahertz. And then I plotted these 5 equations. So you can take a look at these equations. From the Z parameters, you can extract the primary inductance, the secondary inductance, the coupling coefficient, and the quality factor of the 2 inductors. You can easily derive these from the T model that they use for inductors. So if you go back and look at the T model, basically this model. So from this model, you can extract what the value should be from the Z parameters, or you can just use these equations. So if we take a look at the results, we have a primary inductance of about 370 picohenry, secondary inductance of 120 picohenry. The quality factors are 27 and 18, and the coupling coefficient is around 0.69, and this is at 50 gigahertz. So if we take these values back to this circuit and add them in, so I've set the values exactly as what we got from the S parameter file. So these are from the S parameter file. This is the equivalent model values. So you put them back into the simplified model, and then we want to compare the S parameters. So we want to compare S11 with S33, S22 with S44, and then S12 or S21, whichever it doesn't matter, with S34. And that's what I've done down here. So you can see that they are very close. At 50 gigahertz, in fact, they are almost exactly equal. They are exactly equal, almost. So which basically is an indication that even at up to 50 gigahertz, this model, the T model that we use here, which is this one, is pretty accurate. So this basically concludes how you can do the layout for a parametric inductor in HFSS, also for a parametric transformer. In fact, for the transformer, you can also define the a shearing value. So for example, if you want to move these inductors so that the coupling coefficient is reduced, you can do it by simply doing this. You can hide this bottom inductor, remove these guys, and then just select face, select all of these faces, select them from the left side, select all of these faces, right click, edit, surface, move faces along vector, F4, and then you can say Y separation. And then let's say I want to move it by -5 micrometers. Boom. So now you see that basically now you can see that there's a separation between them. And if you increase it, it's 10, it increases even more. But keep in mind that you also need to move this one, this face, so that it's still grounded. So right click, edit surface, move faces along normal, Y, set. Oh, sorry, it should be the other way. Minus face. Okay. So with this, you can also change the separation between them as another additional parameter. And of course, you can move these up. Inner to diameter and so on. Okay, so this way you can basically simulate inductors that are not, simulate transformers with some kind of offset between the two coils to reduce the coupling coefficient if that's what you need in your circuit. And then basically, yeah, export the S parameters. You can take it to ADS and you can analyze what the L1, L2, Q1, Q2, and K are. This basically just covers how to analyze transformers and inductors, how to design them and analyze them. But let's say you want to actually design one for a given value that you get from here. So first, let's say you want to make a transformer that has a certain L1, a certain L2, a certain Q, Q1, Q2, and K. How do you go back and do a layout such that your layout matches those values? That requires some optimization, and I think I'll do a follow-up video on how to set that up. That's also a good example on how you can do optimization in HFSS using optimization routines that are established in MATLAB. So I'll show you how to set up an environment where MATLAB and HFSS can communicate with each other, and you can run optimization routines in that environment. But this should conclude this video. Hopefully it's useful. If you have any questions, please you can leave them in the comments, or if you have my email, you can just send me an email. Thank you.